Hello friends, I welcome you in lecture number 3 on ring theory. In this lecture we will discuss this question on ring which was asked in GTU Winter 2020 exam. So the question is define ring, that is you have to write the definition of ring which we have discussed in lecture number 1. Then show that the algebraic system Z9 with respect to these two binary operations, addition modulo 9 and multiplication modulo 9, where Z9 is the set of equivalence classes generated by integers 0, 1, 2, 3 up to 8. So we have to show that Z9 is a ring under these two operations of addition and multiplication of congruence modulo 9. So as we have discussed in earlier two lectures, that if we have some non-empty set, say R, and if we want to prove that R is a ring, we have to show that R with addition operation is abelian group, and we have to show that R with another operation which we call as multiplication is a semi group, and we have to show that operation of multiplication is distributive over addition, that is a into b plus c equal to ab plus ac, and b plus c into a equal to b into a plus c into a. Here our set R is set of all equivalence classes generated by integers 0, 1, 2 and so on up to 8. And some authors are ignoring these brackets. They simply write this as set of integers up to 9, but as we know that this is not set of only integers from 0 to 9, it is this set of equivalence classes generated by 0, 1, 2 up to 8. Here it is up to 8, and the operation of addition modulo 9 is defined as, if we consider two equivalence classes, and this is equal to a plus b modulo 9. So we have to find out the remainder when a plus b is divided by 9, and this right hand side is the equivalence class generated by remainder when a plus b is divided by 9. Similarly, multiplication modulo 9 is defined as equivalence class ab modulo 9. So here we will write the equivalence class generated by the remainder when a into b is divided by 9. So we must be clear about the definition of this addition modulo and multiplication modulo. So with this in mind, we can show that Z9 is a ring under the operations of addition and multiplication modulo 9. So first we show that Z9 is an abelian group with respect to addition modulo 9. So for that we have to check 5 properties, and for that, because this is a finite set, first we have prepared the multiplication table or composition table for this Z9 with respect to addition modulo 9. So this is the multiplication or composition table for given set with respect to addition modulo 9, and here we have used the fact that if we are interested in a plus b modulo 9, then this is equal to remainder when a plus b is divided by 9. For example, if I am interested in 4 plus 7, so 4 plus 7 is 11, so I have to divide 11 by 9, and let me divide 11 by 9 and I will obtain 2 as the remainder. So here I have written 2. So this is the way how we have prepared this composition table. If addition of two integers is less than 9, then we will write that quantity as it is. For example, 0 plus 0 is 0 because 0 is less than 9, then 0 plus 1 is 1, 1 is less than 9, similarly up to 8. Then 1 plus 0, 1, 1 plus 1 is 2, 1 plus 2, 3, 1 plus 3, 4, 1 plus 4 is 5, 1 plus 5 is 6, 1 plus 6 is 7, 1 plus 7 is 8, and then 1 plus 8, it is 9. So 9 is not less than 9, so we have to divide 9 by 9 and we find that remainder is 0. Similarly, if we are interested in 3 plus 8, if we consider 3 and 8, then we will have 3 plus 8 equal to 11. So we have to find out remainder when 11 is divided by 9, and answer is 2. Suppose we are interested in 7 plus 8. So 7 plus 8 equal to 15. 15 modulo 9, and if we find out, if we divide 15 by 9, remainder will be 9 into 1, 9, that is 6. So 7 and plus 8 is written as 6. So this is the way how we have prepared this composition table using this operation. A addition modulo 9, B equal to remainder when A plus B is divided by 9. So once we have composition table, we can easily check, or we can easily see that all the properties for abelian group are satisfied. We will discuss all the properties one by one. First property is closure property, which says that if we take any two elements, then if we apply addition modulo 9 on that element, then resulting element must be in Z9. So we can see all the entries in the table are elements of Z9. If we take any entry in the table, then it belongs to Z9. So we can say that if we take any two elements of Z9, then A plus B modulo 9 is also in Z9. Therefore closure property is satisfied. Then we have to prove associative property. Associative property says that if we consider A plus B plus C with respect to addition modulo 9, and if we consider A plus B plus C, then this must be equal for any three elements A, B, C of Z9. So this will also be automatically satisfied because all these are integers, and for integers addition modulo is commutative. We can simply check for one or two, we can check for particular values of A, B and C. Suppose I consider A equal to 3, B equal to 4 and C equal to 7. Then if I want to check A plus B plus C, that is under addition modulo 9, A equal to 3, B is 4 and then plus C. So first we write what is 4 plus 7. So we observe at 4 and 7. So intersection point. This is 7. This column corresponds to 7. This row corresponds to 4. So 4 plus 7 is 2. And then we find 3 plus 2. So 3 and 2 here. So we can obtain 3 plus 2 equal to 5. Now we find out other part, that is A plus B plus C. If we check for this, then this is equal to A is 3, B is 4 plus 7. So first we write 3 plus 4. This is 3 and 4 here, so 7, and 7 plus 7. So 7 up to 7, that is 5. So we can see for these three values of A, B and C, associative property is satisfied. So in this way we can prove that associative property is satisfied for all the elements of Z9 with respect to this addition modulo 9. But it is very time consuming to write down this property for all possible values of A, B and C. But we can simply say that All addition modulo 9 is associative operation, therefore we can write this directly for any ABC belongs to Z9. Next property is identity with respect to addition modulo 9 or 0 of ring R. We know that if we consider identity of given ring with respect to addition operation, then it is known as 0 of R. So we have to search for that element such that A addition modulo 9 and that element equal to A for all values of A in Z9. So we are interested in value of E. Which element out of 0 to 8 will serve this property? E plus A. So from the table it is clear that if we consider E equal to 0, then we will get our element back. We can see 0 plus 0 is 0, 1 plus 0 is 1, 2 plus 0 is 2, 3 plus 0 is 3, and so on. 8 plus 0 is 8. Similarly, we can check in reverse way. 0 plus 0 is 0, 0 plus 1 is 1, and so on. Therefore, 0 is the additive identity, or we can use our that technique that identify the row which is identical to this row. So this is identical to this row which we have written in the heading part. And similarly find out the column which is identical to this column. That column is first column here, and find out the intersecting point of this row and this column, and it is 0. So 0 is the additive identity. So in this way we can decide this 0 of ring R. Here 0 of ring R is element 0 or equivalence class generated by 0. So that I have written here. From the table we find that A addition modulo 9 0 equal to 0 addition modulo 9 A equal to A for any A in the Z9. So 0 is the 0 of Z9, and remember this is not 0, it is equivalence class generated by 0, is the 0 or additive identity of Z9. Now next property is existence of inverses. So once we have identity or 0, we can check the inverse for each and every element. We recall that if I have any element A in Z9, and if I can find out other element B from Z9 such that A plus B equal to B plus A equal to identity, that is 0, then B and A are inverses of each other. So we will check for inverse of each element. So we start from 0 and we search for identity element in the first row. So we obtain 0 here at the very first place. So we can see that 0 plus 0 equal to 0. Therefore inverse of 0 is 0 itself. Then we check for 1. So again we search for identity element in this row, and here we obtain 0. That is 1 plus 8 equal to 0. And we can check here also 8 plus 1 is also 0. Therefore 1 and 8 are inverses of each other. Similarly for 2 we obtain 0 here, that is 2 plus 7 equal to 0, and if you observe 7 plus 2 is also 0, that is 2 and 7 are inverses of each other with respect to addition modulo 9. Similarly for 5 we obtain 0 here, that is 5 plus 4 is 0, and for 4 we obtain 0 here, that is 4 plus 5 is 0. So 4 and 5 are inverses of each other. Similarly for 6 we obtain 0 here, that is 6 plus 3 equal to 0, and 3 plus 6 is also 0. So 6 and 3 are inverses of each other. And for 7 we have already discussed 2 and 7 are inverses of each other. and inverses with respect to addition operation are called negatives. In the algebraic structure ring, we use the word negative of A for the additive inverse or inverse with respect to addition. So here I have written all these things which I discussed, that 0 has inverse 0, 1 and 8 are inverses of each other, 2 and 7 are inverses of each other, 3 and 6 and 4 and 5 are inverses of each other. That is, every element of Z9 has a negative or inverse with respect to addition modulo 9 in Z9. Therefore, Z9 is a group with respect to addition modulo 9 that we have proved. This is a group. Now we have to check commutative property also, because we want to prove that it is an abelian group. So for commutative property, we can consider the diagonal of the table, and if we draw the line starting from this, so this is the main diagonal of the table. Now for commutative property, we have to check whether entries in the table are symmetric with respect to this main diagonal. So we can start checking from this. Here if I check here, then I have 1 1, so these entries are symmetric with respect to this diagonal. Similarly, we can see 2 is here, then 2 is here. So if we draw the line perpendicular to this diagonal, we obtain 2 here. Similarly, we can draw the line perpendicular to diagonal. We have 3 3 3 3 here. Similarly, I have 2 times 4 here. Here also I am having 4 2 times, then 5 2 times, 3 times 5. So here also 3 times 5, then 6 6 6 3 times. Here also 6 6 3 times, then 7 7 7 7. Here also 7 4 times, and you can see similarly all the entries are symmetric with respect to main diagonal. If we draw the lines perpendicular to main diagonal, we can observe that entries are symmetric with respect to main diagonal. This shows that Z9 is an abelian group. Commutative property is satisfied. So that also we have mentioned. Observe that all the entries in the table are symmetric with respect to main diagonal. Therefore, Z9 is an abelian group under addition modulo 9. Now we have to prove that Z9 is a semi-group under multiplication modulo 9. So again we have to prepare the table for multiplication modulo 9. So that I have prepared here. Here we will use the fact that if we consider A multiplication modulo 9B equal to, then I have to find out the remainder when A into B is divided by 9. So using this definition of multiplication modulo, I have prepared this table. For example, if I am interested in the multiplication of 5 and 7, then I have to find out remainder when 35 is divided by 9. So 35 divided by 9, and 9 into 4 is 36. So I have to write 9 into 3 27, and I obtain 8. So we can see 5 into 7 is 8. So in this way I have prepared this table using this definition. A into B equal to A into B if it is less than 9. Otherwise, find out remainder when A into B is divided by 9. For example, 3 into 2 is 6. 6 is less than 9, so I keep 6 as it is. But 3 into 7, that is 21. So I have to divide 21 by 9, and I observe that remainder is 3. So here I have written 3. So in this way I have prepared this multiplication table or composition table for multiplication modulo 9, and we can observe that all the entries are in the set Z9. So we can say that A into B is an element of Z9 for any two elements A and B of Z9. That means Z9 is closed with respect to multiplication modulo 9, or closure property is satisfied. Clearly, for any AB in Z9, AB is also an element of Z9, therefore Z9 is closed under addition modulo 9. Now we have to check second property, which is associative. That is, we have to show that A multiplication modulo 9, B multiplication modulo 9 into C, and if we change the grouping A, B and C, then this must be equal. So as in the case of addition modulo, multiplication modulo is also always associative. So we can directly write that we know that multiplication modulo is associative, therefore A into BC equal to AB into C for any ABC belongs to Z9. Therefore this multiplication modulo is associative. If you wish, you can check by considering particular values of ABC as I have taken for addition modulo 9. So this also we will write directly. Last property is distributive property, so that also we will write directly. We know that multiplication modulo is distributive over addition modulo, that is A into B plus C equal to AB plus AC, B plus C into A equal to BA plus CA for any ABC belongs to Z9. If you wish, you can check by taking particular values of A, B and C. So in this way we have to write all these properties systematically, and we can see all the properties are satisfied. Therefore Z9 under addition modulo 9 and multiplication modulo 9 is a ring. So this question was asked in winter or summer 2000, let me check, winter 2020 exam, and this type of questions they can ask you. Show that given set is a ring under the given binary operations. Now this is not true for Z9 only. In fact, if we consider any set for n belongs to n, we know that Z9 is the set of equivalence classes generated by 0, 1, 2 up to n minus 1. So remember, for any natural number n, Z9 is a ring under addition modulo Zn is a ring under addition modulo n and multiplication modulo n. This is always a ring under this addition and multiplication modulo n. So that I have written as a note, Zm equal to this under the operations of addition and multiplication modulo m is a ring, and this ring is called the ring of integers modulo m. So in this way we can prove that given set is a ring under the given binary operations. So this is all about this session. I hope you like it. Thank you very much.